Hello, everyone. So today we are going to be talking about the Carnot cycle. So the Carnot cycle is essentially a way of talking about how we can predict the maximum efficiency of a heat engine. So heat engines end up being a fairly important feature of modern life as they are a more general description of more or less how your car runs. Most engines work by moving energy from some sort of hot source to some sort of cold source, whether it's a steam engine, a internal combustion engine, or anything, or even just a simple heat pump. These tend to work by moving energy from one location to another and then end up producing work as a side effect. So what we're going to be trying to do is examine the perfectly efficient engine. So as efficient a heat engine as we can possibly get. This is most commonly known as the Carnot heat engine and was originally constructed as a conceptual idea for trying to predict what the maximum efficiency of an engine is, though it has been designed in some simpler forms. And the general point of how the heat engine is going to work is it's going to take energy from some hot source, and then it's going to channel some of that energy out as PV work, so moving a turbine or moving a piston, and the rest of that energy is going to exit essentially as heat to some sort of cold sink. You can often think of this as, say, the atmosphere. And so what we're going to try and determine is the minimum amount of energy that needs to go to this heat sink in order to allow the rest of the energy to actually be used as used as ordered work. And it's not too surprising, this is going to be, by its nature, a topic of entropy. I have some sort of disordered energy coming in as heat, and I'm trying to turn it into ordered work. And this won't be perfectly efficient, as I'm going to need to increase the disorder of somewhere else to allow this work to happen. So the Carnot cycle essentially works by trying to break down an engine into 4 reversible steps. So each of these steps technically would occur infinitely slow to get the most energy out of our heat engine as possible on the expansion and put in as little energy as possible on the compression. Because again, an engine should work as a complete cycle where I return to where I start, which allows me to put energy in and then take energy out. So our 4 steps essentially work by first undergoing an isothermal expansion. So you can assume we have a rather empty piston, which I'm then going to provide, add in heat to the system under a constant temperature under a constant temperature scenario. So in this point, you can imagine putting the piston in a nice hot chamber and allowing heat to flow in and the gas to expand. After that, we have an adiabatic expansion. So I go ahead and insulate my system, removing it from the hot source, at which point we will see some continued expansion of the system as the temperature will essentially decrease. Next up, we have isothermal compression. So now that I'm now at this cold temperature and I've expended all my work, I'm going to go ahead and compress the system by letting heat flow out of the cylinder into essentially some sort of cold sink. And then finally, adiabatic compression. We're now compressing the system even more, but by doing this, I'm going to end up heating the system, as we talked about in the previous chapter. So what we can then do is we can add together these 4 steps of the reaction together, and by doing this, we can look at the entropy change for each step and essentially the amount of work and the efficiency of each step to give us a model of the efficiency for the total process. So let's go ahead and walk through each of these steps individually. So first up, we have our isothermal expansion. So in this case, again, heat's being slowly introduced to the system. So this is going to come from some sort of constant temperature hot source. So you can imagine, say, uh, putting our putting our piston next to, say, a uh, a hot fire, and then letting it essentially expand. So what this is going to end up causing is a expansion of the volume, but we're also going to similarly see a pressure drop, as this is a reversible system. And it turns out we already have a set of equations to model this volume change. So in this case, for an isothermal expansion, for an ideal gas, we know that there should be no change in the internal energy of the system, which means the heat being provided by our hot source is going to be equal to the negative of the work being accomplished by our system. And then we can relate this to the difference in the volumes, where V1 is where we started and V2 is the end of this first stage. However, one of the things that is worth noting is you can actually predict the pressure drop as well using our final volume and our ideal gas law. And then with this expression for the heat being transferred, we can also turn this into the change in entropy of the system, as long as we know what the temperature is of our original heat source. So then that brings us to our next step, our adiabatic expansion, where in this case, our heat's being removed from the system, or energy is being removed from the system as a expansion, as our chamber expands, while no heat is actually being allowed to move in or out. So in this case, we have our classic adiabatic system, where any expansion is essentially occurring at the loss of energy inside the chamber in the form of temperature. And so in this case, we know that the heat transfer is zero, and the amount of work being accomplished is going to be equal to the change in internal energy, which again is going to be equal to CV final temp minus initial temp. So we can use this to predict the change in internal energy as well as the work being accomplished. Similarly, you can predict the volume change using the ratio of the temperatures and the identity of the gas, as we built up previously in our adiabatic expansion and compression section. However, since no heat is being transferred, this means that our change in entropy is going to be zero, as essentially because no heat has entered or left, the system really hasn't become more or less disordered, just differently ordered. Then that brings us to the next step of isothermal compression. So this is kind of the flip side of our first step, where we're now going to be removing heat from our now colder system by putting it in contact with some sort of colder environment. A typical choice here is just the room temperature atmosphere, which is indeed much colder than, say, a hot fire. And so while this heat is being removed, we're essentially also going to be putting extra energy into the system in the form of work. So we'll now be essentially compressing our piston back down. And it turns out that because this is isothermal, the amount of work we put in is going to be the exact negative of the heat leaving the system. So again, all energy coming in is essentially just leaving in a different form. And again, using what we know of isothermal reversible compressions, we can go ahead and relate the amount of heat leaving the system to the difference in the volume. Now, one of the other things that is worth noting is because we know the amount of heat leaving the system, we can also relate this to the entropy of the system. Now, one of the things I want to make note of is in this case, we are going to have a negative heat as energy is leaving the system, which means we have a negative entropy. So essentially, as I'm compressing the system, I'm making the system more organized and essentially have fewer microstates it can occupy as it's become more ordered or more confined. And then our final step is the adiabatic compression. So in this case, I go ahead and remove my remove my piston from contact with my cold source, but I still keep adding energy into the system in the form of work. And as I apply work to the system, we're also going to similarly see a an increase in energy of the system, which is going to exhibit itself as temp, as this is, again, an ideal gas. So again, we can model the amount of energy being put into the system based on the buildup of temperature using our expression for the change in internal energy of the system via the difference in temperatures. And again, we can use our equations for adiabatic compression to figure out the ratio of our volume differences based on the differences of temperature in between our hot and cold sink. However, one of the things that is worth noting is that since there was no change in heat, again, we see no change in entropy of the system. So what we can then do is try and take a look at our Carnot cycle in terms of the entropy. And again, since I am in a closed system, we should expect our entropy to return to where we started. So all of our terms added together should give us a net entropy change of 0. So our isothermal expansion is going to be related to the amount of heat being put into the system and the temperature under these hot conditions. Similarly, when I have my adiabatic expansion, I see a reduction in temperature, but no change in entropy. My compression, I'm going to see a ordering of the system, so a reduction in entropy, but no change in temperature. And this is going to be, again, related to the amount of heat that leaves the system. And again, for our adiabatic compression, we're seeing a heating of the system, but no change in entropy. So you can often represent our Carnot cycle with this temperature entropy graphical representation, where we see alternating temperature changes and entropy changes. Now we can go ahead and add all of our entropy terms together. And here we get lucky because 2 of our legs are 0. So our total entropy is simply going, our total entropy change of the system is simply going to be the addition of the ratio of the energy added from our hot source times the temperature divided by the temperature of our hot source, plus the energy that exits into our cold sink divided by the temperature of that cold sink. Now we can then go ahead and rearrange this expression. And what we see is that these 2 terms will have to be equal in value, but opposite in magnitude for, again, this ideally efficient engine. And we can also go ahead and rearrange this expression to give us a ratio of the heats in terms of a ratio of the temperatures. And this actually shows us a very important feature, which is the fact that since my hot temperature, by definition, has to be larger than the temperature of my cold sink, because again, hot and cold. This also means that the amount of energy that enters the system in terms of heat is also going to be larger than the amount of energy that leaves the system going to the cold sink. And the greater this ratio, the greater the difference in these heats. Now, this becomes very important because if this energy isn't leaving as heat, it means it's leaving as work. So this is going to tell us a lot about how much work my system can accomplish. So let's go ahead and look at this idea a little bit more in detail by looking at the amount of work accomplished at each step of this reaction. So again, for my isothermal expansion, the work being accomplished by the system is going to be the same as the absolute value of the heat entering the system. It is worth noting that this heat value will be negative, but our work being accomplished in this expansion step is going to be positive. For the adiabatic expansion, we're also going to see our system accomplishing work, but this work is going to be related on the difference in the temperatures. And our isothermal compression, essentially, we're putting work into the system of an equal but opposite magnitude of the heat essentially leaving. And then again, for our adiabatic compression, we're seeing essentially all of the work being driven by the change in internal energy, which is related to the difference of our hot and cold temps. So we can then look at the net work performed by the system by adding together these four parts. And at this point, we actually see something quite special that starts to emerge. Because our adiabatic expansion and our adiabatic compression terms, well, they're just equal but opposite in signs. So the same amount of energy that enters the system in stage 4 is going to be the same amount of energy that leaves the system in stage 2. So these two will just cancel out. And so the work being accomplished by the system is essentially just going to be the difference in between the amount of heat entering the system in stage 1 and the amount of heat leaving the system in stage 3. So again, this actually should make sense based on what we previously saw, that all energy, that based on the first law, anything that isn't going to be heat entering or leaving the system is going to be expressed as the work being accomplished by the system. And so using these, this idea of work, what we can then do is try and determine the efficiency of our system. So the efficiency of our system is going to more or less be the ratio of the amount of work performed by the system over the amount of heat absorbed by the system. So essentially, this is the energy that I put in, and here's the energy that I get out as a usable form, with the remainder going to essentially the cold sink as unusable energy. And so again, an ideally efficient system would have this ratio being 1, but we never quite get there, because what we can do is insert our expression that we just derived for the work accomplished by the system as the difference in between the magnitudes of our two heats divided by the magnitude of the heat entering the system. So we'll notice that these two terms will end up canceling out to a value of 1, and then we essentially are just subtracting out the ratio of the differences of the heats. But we also previously showed with entropy that the ratio of the differences of the two heats is going to be the same thing as the ratio of the differences of the two temperatures. So this actually ends up showing us a rather cool feature, is that the efficiency of a heat engine is going to be entirely based on the ratio of the temperatures of our hot source and our cold sink. So if my hot source and cold sink are the same temperature, say I'm trying to run a piston based on room temperature air with the energy then going to a room temperature air, well then these two values are the same. We get a value of 1, and the efficiency of the engine is 0 because it can't do any work, which is, a little problematic. However, let's say I have a great roaring fire and very cold atmosphere. Well, then this efficiency is going to get much better. And so generally what we're going to be finding is the greater our temperature differences, the more efficient the engine. So for example, if you wanted to think of one of the best places to essentially make use of a heat engine, well, a great place might be to try, say, space, because it turns out the sun is really hot and space is really cold. So there's a lot you could do out there. But again, one of the other things that is really nice about the Carnot cycle is more or less all it really assumes is reversibility. And so any reversible engine is going to have the exact same efficiency. So we're always going to be approaching the same ideal point. So if you want to figure out what the maximum efficiency is of any engine, you can use this same expression we derived from our Carnot cycle to get an idea of what's the best you can do based on entropy and not just the first law. So hopefully this was helpful. Next time, we're going to be diving into a little bit more on some applications of entropy, specifically looking a little more in detail at some compressions and expansions. Till then, take care.